Welcome back to Physics Fundamentals. In this video, I want to talk about properties of sound. At the most basic level, sound is a wave. Specifically, it is a wave propagating through a material that can reach our ears and be interpreted. So the material that can reach our ears is almost always air. Occasionally something else. If you are underwater, then sound can propagate through the water and reach your ears. If you press your ear against a door, the sound can propagate through the wood of the door and reach your ear, but those are kind of the exceptions, the corner cases. And then our ear interprets sound by detecting specific frequencies. The frequencies that your ear can detect will vary wildly from person to person. When you are born, you have a lot larger a range of hearing than when you are an adult, because the act of hearing sound actually damages the device that is meant to hear sound. But the general rule, the accepted range, is that people can hear between 20 hertz and 20,000 hertz. When we detect hearing, or when we detect sound, when we detect the frequency, we detect what musicians call the pitch of the sound. So, for example, if I sing down here, that's somewhere in the ballpark of 130 hertz. And then if I sing higher, from here to here, that's about 260 hertz. The rule of thumb that musicians use is known as A440. A440 means that a particular note, what musicians call the A above middle C, has a frequency of 440 hertz. And so just because it's a nice reference point, I'm going to use 440 hertz in a lot of our examples. So, when we're talking about sound, another interesting thing we want to talk about is the speed. The speed of sound depends on both the media that the sound is passing through and the temperature. So I have to say something like the speed of sound in air at 0 degrees Celsius. We'll use the lowercase u to represent a wave speed, and the speed of sound in air at 0 degrees Celsius is 331 meters per second. Our quick example here, I said we were looking at a frequency of 440 hertz. We have the wave speed of 331 meters per second. And so from that, using what we've talked about previously with sound, we can calculate the wavelength. Well, we know that if we multiply frequency times wavelength, we get wave speed, which means that wavelength is wave speed divided by frequency. So in this case, that's going to be 331 meters per second divided by 440 hertz. My calculator tells me that that is 0.75. And then let's see, we have meters per second divided by hertz, and hertz is 1/second. So the per second and the per second will cancel each other out, leaving me with units of meters. So at 0 degrees Celsius, the wavelength of the 440 hertz A is 75 centimeters, 0.75 meters. When you're dealing with temperatures that are relatively near zero, there is actually a convenient formula. If you take that 331 meters per second and you add to it 0.61 meters per second Celsius degree times the temperature. And here, the temperature is actually measured in degrees Celsius, not in Kelvin. We don't need to go to an absolute scale for this. But if you are relatively close to 0 degrees Celsius, this formula will give you the speed of sound at that temperature. I want to stick with our example. We're looking at the 440 hertz A, and this time we're going to look at the temperature of a warm day, 25 degrees Celsius. And we are again looking for the wavelength. All right, well, with that temperature, we can calculate the wave speed. In this case, 346 meters per second. All right, notice here that the 331 is rounded to the nearest whole meters per second. So when we do this calculation, we're going to round our result to the nearest whole meters per second to match. Okay. Now that we have that wave speed, we know that the wavelength is the wave speed divided by the frequency, which is 346 divided by 440. Right? The frequency does not change because our ear detects the frequency of the wave as pitch. So if we want the same pitch, we need the same frequency. The wavelength is allowed to change. But if I take 346 divided by 440, in this case I get 0.78. Right? So on a warmer day, the wavelength is ever so slightly longer. I don't have a nice formula for any other sorts of speed of sound, but we can always look up, right? In water, which is at 25 degrees Celsius, I can look up on a table and find that the speed of sound is 1,500 meters per second, measured to the nearest 10 meters per second. And so, if I continue to look at my frequency of 440 hertz and look for the wavelength, well, the formula is still wavelength is speed divided by frequency. And if I take 1500 and divide by 440, I get that the wavelength of the sound in water is 3.4 meters. So the frequency or the pitch of the sound is how we distinguish between a soprano and a bass, how we distinguish between a violin and a cello. The other experience we have with sound is the loudness. I can change how easy it is to perceive the sound that I am making by changing its loudness. But it's really a poorly defined measure, right? How easy it is to perceive the sound. Well, human perception is not something we can measure. So instead, we need something that's a little bit more mechanical. So mathematically, we talk about the intensity. Right? The formula here is that intensity is power divided by area. And this gives us an objective tool, right? We can devise devices like a microphone that detect the power of sound. We can then figure out how much area the microphone covers and divide those to turn it into intensity. right? The area here is important, right? If you think about just everyday life, if you cup your hand around your ear, it increases the area where you are able to perceive sounds coming towards your ear from one particular direction, which makes it easier to perceive the sound. So we want that to be fair when we measure intensity, so we take that area and we divide it out here. Power is usually measured in watts. Area is usually measured in square meters. And it turns out that the threshold of human hearing is somewhere on the ballpark of 10 to the negative 12 watts per square meter. That's a really ugly number. And as we look at a couple of other intensities here, we're going to see that the scaling is just completely crazy. A whisper, a soft whisper, is generally on the order of 10 to the negative 9 watt per square meter. I'll just give a couple of other classic examples. Something on the order of 10 to the negative 5th watts per square meter is city traffic. Right? Not being in traffic, but being in the city and hearing the highway going past. And how about one more? At about 10 to the negative 1st watts per square meter, that's your car horn. Specifically, I mean you are close enough that you are in your car hitting the horn, and that's the intensity that you're going to hear. Right. This is an exponential scale. Right? The power on 10 raised to a power is the thing that is interesting about this measurement, because it goes over such a ridiculously large range of possibilities. So another scale for understanding sound was developed. It's called the decibel scale. Right? Deci means it's based on a power of 10, and bell is for Alexander Graham Bell, the inventor of the telephone, who also invented this scaling, this measuring system. And he defined 10 to the negative 12th, the threshold of human hearing, as 0 decibels. And then these other measurements are going to come in at 30 decibels, at 70 decibels, and at 110 decibels. Right? Those are numbers that are a lot easier to manage. The calculation here, if you have your intensity on the order of 10 to the negative n, actually let's just call it 10 to the n, 10 to the n watts per square meter, the translation is going to be 120 minus, well, I guess it would be plus 10n decibels. So if we start with the threshold of human hearing, where n is negative 12, negative 12 times 10 is negative 120, negative 120 plus 120 is 0. Negative 9 times 10 is negative 90. Negative 90 plus 120 is 30. Right. So this is, if you go onward in your study of mathematics or physics, what's known as a logarithmic scale. It translates something that is happening in the exponent to just a base number. And for phenomena that occur over such a wide range like this, it is definitely a valuable tool. Oops, sorry about that. One last thing for today's video, and that is the Doppler effect. You may or may not be familiar with the name, but the sensation of the Doppler effect should be something familiar to you. If you are in a car and you hear another car driving by blaring its car horn, well, as the car approaches you, you're going to hear the car horn at one pitch. And then as the car passes you, you're going to hear a sudden shift from a higher pitch to a lower pitch as the car goes away. The reason for that is the speed of the car is enough to affect the speed of the wave. Right? So here's a nice visualization. So if we think about this source as a car driving through, right, you can see that as the car is driving in, the new waves being emitted are closer to the previous wave. The peak of one wave is close to the peak of the next because the car is driving towards that wave. On the other side, the peak of one wave is further away because the car is driving away from you. And so we can model that mathematically. This equation was written by the Austrian physicist Christian Johann Doppler, and it says that F star is equal to F naught times the quantity U over U plus or minus V. And the variables here. F star is the perceived frequency, and F naught is the emitted frequency. U is the speed of sound, right? Generally the speed of sound in air, or again, whatever medium you happen to be in. V is the source speed. Right? How fast is the car going whose horn you are hearing? And then the last thing we have is this choice of plus or minus, which is closely tied to the source speed. If the car is moving away from you, we're going to choose plus. And if the car is moving towards you, we are going to choose minus. All right, so how about an example? Let's consider a car horn. Almost every car horn of almost every car manufactured in the United States has a horn with a 340 hertz pitch. This is musically an F, and there's usually more than one frequency in a car horn, but this F is usually one of them. And the reason that we do that is so that if everyone in a traffic jam is blaring their car horn, you don't hear conflicting pitches that grate at your ears more than just the loudness of the horn itself. All right, let's say that our car is going at 45 miles per hour. We'll have to convert that to meters per second in order to do anything with it. And let's say that we're outdoors on an 18-degree day. There's a lot more going on here than it seems at first glance. Because again, the first thing we have to do is convert from miles per hour to meters per second. And 45 miles per hour is 45 miles over 1 hour. 1 mile is about 1,609 meters. And 1 hour is 3,600 seconds. So if I grab my calculator, 45 times 1,609 divided by 3,600, that comes out at about 20 meters per second. Up next, the speed of sound. I gave this formula earlier, we've used it once. The speed of sound is 331 plus 0.61 times the temperature in degrees Celsius. In this case, that's 18. 331 times 0.61, 331 plus 0.61 times 18, my calculator tells me, is 342. All right, so there is our speed of sound. The frequency that we are given here is the frequency emitted by the horn. That's what our formula for Doppler shift says is F naught. And then F star is the pitch that we hear. All right, so F star is equal to F naught times U over U plus or minus V. And I'm actually going to do two cases. I'm going to do the plus case. And I'm going to do the minus case. So just plugging in our numbers, let's see, 340 times 342 divided by 342 plus 20. My calculator tells me that this is come on. 321 hertz. And if I put in the other direction, switch that plus to a minus, I get 361 hertz. Kind of coincidental that they are such similar looking numbers, but that gives us what we expect. Right? As the car is coming towards us, the waves shrink, the frequency increases, and we hear a higher pitch. As the car is going away from us, the waves stretch out, the frequency decreases, and we hear a lower pitch. All right. There was a lot in this video. I've covered a lot of ground. Hopefully a lot of it is things that make sense to you. The mathematics aren't that bad, and the sensations, the observations are things that we've experienced in our everyday lives. But in any event, I think that's more than enough for this video, so thank you for joining me, and I'll see you next time.